this one down here. Okay, great. So these are the two motivators for this talk. As Dick mentioned, this ongoing trial that has just begun relative to the earthquake in L'Aquila, Italy, which will resolve, at least under Italian law, what the obligations of scientists are to say what can and can't. Basically, the quick summary is that this is the Central Apennines seismic belt, which is known to be an active area. And in about 2008, the number of earthquakes in a certain area of the town of L'Aquila started to increase with time. And so the question is, and the government committee was asked to say, well, is there a very high probability of an earthquake? And they said, well, what the committee actually said is a little murky. Afterwards, in public statements, some members of this group, I don't mean all of them, said, well, they didn't think it was very large at all. Everyone that's looked at it agreed that even knowing what you know, namely there had been a small increase in the background earthquakes, the statement that one could convert this to a higher probability of an earthquake was extremely low, even if one understood the physics, which one doesn't. But this is now in court. The one in Japan, of course, this is the tsunami from the Tohoku earthquake of March. And what this thing is going over is a 10-meter high seawall, which was, remember, 10 meters, 30 feet, that had been built in many areas of the coast to protect the cities against it. Considerable confidence was placed in these seawalls, and certainly hundreds of millions of dollars, if not more, was spent on this enterprise. And as you can see, the tsunami is just quite happily going over it, doing incredible damage along the coast, including, of course, causing the damage to the Fukushima nuclear power plant. So this brings us the question, which I thought was good to throw out to the group, especially for students thinking about interesting questions, is, you know, we've been at this for 100 years, and why are we doing so badly at it? So basically, I'm just going to try, I'm not even trying to tell you the answers to this, just to try to show you just what a challenge this is. And we haven't made a lot of progress since Charles Richter many years ago said that only fools and charlatans predict earthquakes. We still try, but it doesn't seem to work very well. So quick background, and I'm very pleased to have Dave Jackson here because he was involved in this stuff before I was, pointing out the problems thereof. In the 1970s, when I started graduate school at Caltech, the kind of seismological establishment was announcing that within roughly 5 years, we'd be able to predict earthquakes. And they have a technology as at hand, according to the U.S. Senate, and the federal government said the age of earthquake predictions is upon us. Now, those of my generation pretty much put these statements in at the same time. This is 1970. Is the government statement that victory in Vietnam was right around the corner. We could see the light at the end of the tunnel. And to a lot of us, these two things kind of became merged. It was more or less the same people telling you the same thing. Obviously, it was a fiasco. Let's talk about why that was. What would one want to do? At least we've agreed on what we'd like to do. We would like to specify the location, time, and size of an earthquake before it happens, with the before it happens being a rather crucial constraint that's often violated. One would hope to either make long-term forecasts, use earthquake histories to predict the next one, either from some sort of on a statistical basis, more or less the kinds of things that we were seeing in the climate community, or try to use the rate of motion accumulating across the fault and the amount of slip in earthquakes to make some statements on some physical basis about when they happen. So the other possibility is to do it in a very empirical way, to find precursors, changes in the earth before earthquakes that were consistently resolvable from the normal variability. In other words, there's a very strong tendency to post-date earthquakes and say that, well, if you knew that that was going to happen. Ideally, one would want to do this beforehand and to have something that you can actually consistently resolve. This, in a sense, is the L'Aquila earthquake problem that people say, well, gee, these were now foreshocks to large earthquakes. And the answer is that appears to have been the case. On the other hand, we've never found a way of saying that except to wait for a big earthquake and say that, well, the ones before it were foreshocks. Not very useful. Obviously, the challenge is to do better than you get from purely random, the traditional test. We know a lot about the statistics of earthquakes in some very general regional sense. They obey a kind of standard log linear sort of fractal distribution where as you go up one magnitude unit, earthquakes become 10 times less common. So you can make statements about how often something will be. So, for example, taking the whole the the Earth, you get about one eight every year, about 10 sevens, and about 3 sixes, and so on and so forth. And you can make similar statements in any particular place. So the challenge is to do better than that. Normally, most cases, it turns out they haven't. It's been a post-diction process, somewhat like the old Texas sharpshooter thing where you shoot at the barn and draw circles around the bullet holes. And there's been a very, very strong tendency to do that in the geoscience community. So the question is, can one do better than this? There have been a lot of efforts, and they haven't done well. But so let me sort of walk you through the history of this. Our attempts to do this more or less started in 1906 after the big San Francisco earthquake. This came shortly after the invention of the seismometer, and so this earthquake was actually quite well reported by seismometers. And people started the organized study of earthquakes at that time, and they discovered something absolutely amazing. For a couple hundred kilometers, they discovered a consistent pattern of things that had been offset by about 4 meters. And this zone became recognized as San Andreas Fault, which at the time people hadn't even known it existed. They thought about this for a while and concluded that what seemed to be happening was that over time, the ground on the 2 sides of the fault was moving. It was, on the other hand, the fault was locked, strain would build up, and eventually you would overcome the friction on the fault and you get an earthquake. So although they didn't have any idea why this was happening, but at least they had this idea of what's called elastic rebound or seismic cycles or something. 60 years later, people realized that this was happening because of San Andreas and features like it were the boundaries between plates, in that case North American and Pacific plates, and so that caused this motion. It's an animation that I didn't bother. Maybe I can easily get out and make it run for you. Okay, I know what point here. I just wanted to kind of motivate something. This is kind of a classic seismological experiment that people always do in classes. It's useful to think about. That's a yoga mat so far. I'm just pulling on a rubber band. This is kind of the thing that every beginning geophysics class uses. And so you're loading a fault, and essentially you're slowly overcoming the friction, the energy stored in the string. But one thing you'll notice is that it's not fantastically periodic. It's sort of periodic. It's sort of quasi-periodic, but it's not fantastically periodic. And we'll see that if you actually look at earthquake time histories, they have that phenomenon that there's a lot of variability in that sort of system. So let's see. This one here? Good. So what this means is that if we have some generalized idea of what's going on, but it's sure hard to predict anything fantastically useful from it. And I'll show you some examples of that. This is routinely demonstrated by the failure of earthquake prediction projects. This is one that Dave here has looked at. This is the most famous one. This is the largest prediction effort in the U.S., where there's a piece of the San Andreas Fault that has earthquakes about every 22 years. And so in 1985, the U.S. Geological Survey predicted with 95% confidence would happen by 1993. It actually happened in 2004, which is 16 years late, which, given that the mean time between them is 22 years, you can sort of say it was overdue, but it gets a little dicey here. Basically, it turned out among other things, they had discounted the fact that this 1934 one didn't fit on the line. They sort of just threw it out to improve the counting statistics. More seriously, this is bad, but what was really worse was that absolutely nothing happened prior to this earthquake. And that's really troubling. In other words, there were no foreshocks. There were no changes in strain. There was nothing observed on magnetometers. There was nothing observed on GPS. There was nothing observed on creep meters. And this, as a result, produced a lot of jokes about the Portfield Park experiment. So it didn't look very good. We now have better ways of making these kind of measurements. These GPSs turned out to be the best one. It can give us millimeter resolution. And some things it does very, very well. For example, it beautifully shows us that strain building up across the San Andreas, this This fence here is drawn in what turns out to be an arctangent function that has that property. You can sort of see that strain building up very nicely. You get about 35 millimeters a year. That's pretty good. If you go longer-term experiments, this is one that's close to our hearts. This is a measurement, the first way people estimating long-term motion on this piece of the San Andreas Fault. This stream used to go across the San Andreas Fault several thousand years ago. It's now been offset. You can date that offset from, and divide that out, and you get that on average, there's about 35 millimeters a year of motion. So this long-term average, or at least several thousand years, and the 1 over 10 years or so is consistent. Interesting enough, this observation was made by one of the more famous NU geology graduates. So it's fun to show for that reason. So that says on average, well, okay, we should have earthquakes about, if you say there's about 4 meters of slip and there's about 35 millimeters a year, you get them in 115 years. The last one was in 1857, so you add that up, you should get that sometime in about 1963, I think, something like 62, 72. And of course, those predictions were made. They're predicting a massive earthquake within the next 30 years and most likely in the next decade or so. Obviously, this earthquake has not yet happened. Then there was a similar claim based on the idea that there was supposed to be large-scale ground deformation that showed that a big earthquake was coming. And again, that was forecast within the next decade, so in 1975. So sometime by 1985, we were supposed to have 12,000 dead, 48,000 injuries, 40,000 damaged building, and 25 billion in damage. Back when $25 billion was real money. Okay. It was 1975, so maybe 100 billion today. Obviously, this earthquake didn't happen, and I would want to, and among the people, David here looked at this question, showed basically this was completely an observational artifact, and none of this phenomenon existed at all, apparently. So, obviously, the first part of this, and I suspect most of you can tell where we're going, is it looks like we are looking at a system which has no clear evidence for precursors before large earthquakes, and it's led to a lot of the same sort of thinking that the meteorologists are doing, namely that you have these small perturbations growing to large effects. Here the argument has been that probably regularly you'll have tiny earthquakes, only a very small fraction grow into large earthquakes. This being, like the Lorentz business about you flap a butterfly, it swings in Brazil, plus a tornado in Texas. From our standpoint, what it means is that if there's nothing special about those tiny earthquakes that happen to grow into large ones, then the time between large earthquakes is highly variable, and nothing observable should happen before them. Put another way, if the Earth doesn't know which small, tiny earthquakes are going to go into large ones, it has no way of telling us. That suggests that either it's impossible to predict earthquakes, or at least it's nearly impossible to predict earthquakes. And this is just a fun demonstration we do for class, and some people have probably done this one, where you just start off with some very simple function. In this case, it's 2x squared minus 1. You start it with trivially different initial conditions, and you watch the perturbations grow wildly from those initial starting conditions. And this, of course, is more or less what Lorentz discovered accidentally when he was starting to run simple weather models. Back in the 60s, he put a slightly different number in, and all of a sudden the model produced wildly different numbers. So this probably is what we're looking at. So the first half of this is we don't seem on any way near to predict earthquakes. There's nothing that makes it look possible. And at this point, unless someone gets really clever and thinks of something which no one else has thought of, it doesn't look like anything's going to happen. So that part seems to clearly have been. The next part is to see if we can do better in terms of making longer-term forecasts. And that's what the engineers and hazard mappers use. They use maps developed by seismologists, and these predict the hazard. Now, an earthquake hazard isn't something you can measure. It's not like little g. It's something you compute according to some model. It's defined as the maximum shaking you expect to occur in some time. So this is the U.S. government's map, which drew my interest simply because it claimed that the central U.S. was as dangerous as California, which I thought was a fairly plausible argument. So we started looking into this, was Memphis, Tennessee really the most dangerous place in the United States for earthquakes? And that leads you to ask how they do these things. The first thing they say is, we have great confidence in our hazard mapping methods. And so you say, okay, let's see how they look in other places. So then once you start looking, the answer doesn't seem very good. This is Haiti, where this is the 2001 map. It showed that the maximum shaking you'd expect in the next 500 years was something on 6 on what's called an intensity scale, which amounts to light damage to at least decent buildings, which is not the case, of course, in Haiti. In fact, what one got within 10 years was one got intensity 9. So that doesn't look very good. But the truly spectacular thing is this lump had been swept under the rug aggressively for a while, and really brought it home was the Tohoku earthquake. This is the seismic hazards map which Japan prepared in January 2010, and basically the red are places that are at great danger of damage, and the yellow are fairly low ones. This is where the Tohoku earthquake, which was a magnitude 9 earthquake, occurred, and in other words, the map had clearly not at all done a good job of predicting what was going to happen. It's been pointed out that this seems to be a sort of endemic problem. Earlier versions of it seem to miss other earthquakes. So it was fairly clear that at some deep level something is wrong with this stuff, and that the error standards are much larger than anyone thinks they are. To try to get a sense of how big that difference is, this is a graphic showing you the difference between a magnitude 8 earthquake, which is what the Japanese planners expected. This box would be the size of a fault. The arrow would be the amount of slip on it. For magnitude 8, you'd expect about the order of 5 meters of slip. Tsunami run-up is about twice that. So this would be a 10-meter tsunami, which wouldn't have done so badly. What they got was a 9, which is a significantly larger fault, with much larger displacement, which as a result had no trouble getting over these seawalls. If you have any doubts, take a guess as to how high that minivan is. Somebody guess? 2 meters? Okay, how many minivans could you stack up that seawall? Between 4 and 5 of them. So this, and you can see it, the tsunami had absolutely no trouble getting over that stuff. So then the question was, my colleague O'Connor looked into why this came out so wrong, and there are a bunch of different things went into it. It's almost a perfect storm that hit them. Everything that could conceivably go bad in terms of hazard forecasting that happened. One of them was there was a conceptual picture that had grown up which said that you could only get these giant magnitude 9s in places where you had young plate, which is hot and hence thermally buoyant, subducting at a very fast rate that is pushing into that trench here where you get the earthquake. That in turn would be very tightly coupled here, and you need that for big earthquakes. That idea was fairly common. And then after the 2004 Indian Ocean tsunami produced by the tsunami earthquake, we realized that no, you don't have to be up in that corner here. Now when this was over in that corner of it, we now realize that basically this pattern was just pure coincidence that just happened to jump out of a few earthquakes. There's no underlying pattern here. What seemed to happen is that bigger earthquakes involve longer pieces of fault, in this case the subduction zone trench breaking. These 8s are more common than the 9s, and we have a sufficiently short record that we saw a few of these and said, only a few special places can have these. In reality, it looks like just about any place with a big enough trench can have them. So it looked like they just hadn't appreciated how big that could be. To get a sense of how this works, tsunamis radiate just about all their energy at right angles to a fault. This is the area that slipped off the Tohoku coast, and you can see this is a 10-meter run-up height. And you can see all in here, you got well over 10 meters, some places over 20. You might see so an enormous tsunami came ashore here. The other thing that was true that the Japanese had done is, for complex reasons, they discounted their own historical record. They knew for certain that in 1896 they had tsunamis that went over 20 meters. And in fact, if you go back to like the 869, they're much bigger. There's actually a cultural thing. These stones were up on some of the hillsides, and it said, "Don't build your house below this point." That's been left by people in the past, and some towns that followed it did better than the ones that didn't. But so the point is that even with what was known from 1896, it was clear that you could get things much, much higher. Needless to say, this is a huge political uproar because this is tied to the damage from Fukushima, which the damage did enormous harm to the Japanese economy. And although the Japanese historically have tended not to go to court over such matters, They will be fighting this one out in court. It's already essentially caused resignations of a lot of government officials. This is going to be a big issue in years to come. From our standpoint, what it tells us is that this is a hard thing to do. It also forced people to start acknowledging that, here's a nice summary from science. Crystal ball is proving cloudy mostly cloudy around the world. Failing earthquake predictions, seismologists tried to make fuzzier forecasts, but the megaquake is only the latest reminder of the method's shortcomings. So that's kind of troubling, given that this goes into billions of dollars of construction. So what I want to do for the rest of the talk is just kind of give you a few examples of what seems to be going wrong here. We don't know how to cure these yet, but at least we try to parameterize what's going wrong. Turns out these hazard mappers are failing because of bad physics, i.e. they incorrectly describe the earthquake processes. That's what we saw that they couldn't have done. Bad assumptions about what they think could be going on. Bad data, which is they either lack data or they had incomplete data, or in the case of this past tsunamis, they didn't appreciate it, or just bad luck. This is the famous sort of black swan, low probability events, or some combination of these. And a pretty good case could be made that what happened to Tohoku is a combination of all four of these, which is about, as unlucky as you get. So let me quickly walk you through something which is basically an attempt that we've been doing here to try to simulate this process by just looking at hazard maps and generating different assumptions to try to see how well they work. So what we do is they really have to know four things to predict earthquake hazards. They have to know where earthquakes will happen. They have to know when they're going to happen. They have to assume how large they're going to be and how strong the shake will be. Now, if you guess fairly well at these, you'll come up with a pretty good map. If you guess badly at these, your map won't do that well. And these are all pretty hard things to guess right. Where, again, the track record is not good. This is the earthquake hazards map of North Africa. You can see it has big red blobs where you've had past earthquakes in the last 100 years. So, of course, what's happened since then is the earthquakes show up in the low hazard areas. So it's pretty clear that they've been underestimating it. This is an even more spectacular example. This is the Wenchuan earthquake in China. It did enormous damage in Sichuan province a few years ago. That's the Wenchuan fault. You notice it's mapped in this green. It's in fairly low hazard. Well, how did they get themselves to that? Well, they took the places where you had big earthquakes that they knew about, and they colored those red in the places that they didn't have much past earthquakes in the last 100 years or so. They plotted as green. Clearly, this wasn't an adequate time sample. We've done some simple numerical experiments to look at that, and these are just simulations along the coast of Canada. The two largest earthquakes we know of in eastern North America in the last 200 years or so are here in Back Bay in 1933, that's 9.7, here in the Grand Banks of 7.2. So the question is, do you want to say that the hazard of earthquakes is the same everywhere, or do you want to say these are the really dangerous places? We've done real simple numerical simulations of this, and what it says is, at the rate of earthquakes we have now, if you had even 1,000 years of data, you'd say, this place is dangerous and this place isn't. If you have about 10,000 years of earthquakes, remember the seismometers invented 100 years ago, you'd finally begin to realize this was uniform. So that's tough. And this is, you can get wildly different maps depending on what you assume. This is the Canadian map in 1985 where they show big hazard where you had past earthquakes, these bullseyes. The newer version, I think, makes a lot more sense where they're starting to smear that out between them. Okay, last thing I want to show you, I'll show you one more example that's even more impressive. When we go into the interiors of continents, we're not just dealing with one fault, but we're dealing with a lot of faults scattered over a very large area. And it looks like motion moves back and forth between these faults. So we spotted this in the central U.S. where we went off expecting to see evidence of large earthquakes on the way. We made GPS measurements because about 500 years ago, there had been a big earthquake in 1450. That seems to have been a lot like the big one that happened 200 years ago in 1812. There's another one in 900. So this seemed like this was going to go on, and that every 500 years we'd see a big one. So we went out there to make measurements to see what was going on. We found absolutely no ground movement. So we said, it looks like these faults simply switch on and off, and that it's a very non-steady state system. At first, that idea sounded crazy to people, because we have this very steady state view of the world. But the more you look at the continents, the more you see this fault switching on and off. So I want to walk you through our favorite example. This is the northern part of China. We're going to look at earthquakes starting about the birth of Christ. And I'm going to show you a series of movies, of panels here. In each one, you're going to see open circles, which are earthquakes from earlier times, taken from historic records. And then we'll see blue dots, which are the ones that happened during this time window. So let's start here. Let's start off with this period from 1300 to 1350. We'll look just at these huge ones, these magnitude 8s. And you see that this structure here, which is something called the Shensi Graben, that fault system, looks to be really active. So you figure, okay, the next earthquake should be on there, right? Okay, that's another magnitude 8 there. Now we know for sure, we've got 1,600 years worth of data, that this is the really dangerous place in China. Everybody agree? Let's see where the next one is. It's 800 kilometers off to this side here. And then you say, okay, now we know what's going on. Surely this system here must be switching on. Okay, so the next one's got to be here, right? Well, that moves another 800 kilometers up there. This is now 1965. So armed with 1,900 years of data, the Chinese authorities decide they should start predicting earthquakes. They launch a big national program. As I just showed you, the capitalist West has not managed to predict earthquakes, but they have the teachings of Chairman Mao and so on, so it seems like they should probably do better. So let's see how well they do. As you can see, the earthquakes now all move to a very different part of China and a very bad place for them to go to because this is a really populous North China plain. So in fact, no magnitude 7 earthquakes ruptured the same fault segment twice in the past 2,000 years. That's kind of trouble. It doesn't look good for predicting earthquakes. So what they're really doing, what we're doing in this business is kind of like this whack-a-mole game where you whack at the mole, and of course the mole will just come up in a different hole. And this seems to be what most of earthquake hazard assessment amounts to. When it turns out we don't do much better than, I'll do a quickie. This is a time series for that San Andreas. Remember, we worked out that it would have, the earthquakes had to be about every 120 years or so. On average, that's sort of true, but the problem is the mean is about 132 years. The standard deviation is about 105. So you can see that the ability of this to make any fantastically useful predictions is not very great. The statisticians that first tried to work with this said that in the next 30 years, probably an earthquake would be somewhere between 7 and 50%. But that was really an underestimate because it didn't include the possibility of systematic errors, like that you might have missed some earthquakes. They just looked at the form uncertainty. So again, this hasn't happened yet. It's going to be tough. Another thing that we don't know, and I think David is going to talk about this question later in the week, is we still don't have the faintest idea the most basic question of all, which is when the probability of earthquakes is essentially Poissonian, that is, the day after an earthquake you could have another one. That's actually what's assumed in hazard maps, or the probability of earthquakes is slow and it increases with time. We don't know which of those is true. Different studies give you different answers. But whatever it is, you can get wildly different earthquake hazard predictions depending on which you assume. So this is one we've run for the central U.S., and the change is by about a factor of 50% in the city of Memphis, depending on which of those you want to assume. We haven't got a clue which of those is a better assumption. How large they'll be, we don't do a whole lot better at. What we tend to do is use these, p-value curves, these log linear plots, to say about how often the big ones will be. Should be on a nice straight line. Sometimes when you try it, this end bumps up higher. Sometimes it comes down here. There's a lot of complicated arguments. Obviously, this is good if you're in the hazard mapping business because that means they're more hazardous. It seems like an awful lot of this stuff is probably sampling bias. We've done a very simple thing. Obviously, professional statisticians can do better with this than we do. We just generate synthetic earthquake histories, assuming they obey a Gaussian distribution with a mean, and then we just sample them. And of course, in most cases, our sample space, sample time period is really short. So typically, for example, here we're only sampling half the mean time between these magnitude 7 earthquakes. So obviously, since we can't observe half an earthquake, we are, by definition, observe the ones that are biased to this side. So one of two things happen. If we see an earthquake, it's more common than we might think. That happens about half the time. The other half of the time, we don't see a big earthquake at all. And in that other 40% of the time, we say, we don't get earthquakes that big here. Both of these would, of course, be just totally biased conclusions from the sample. Turns out, even if you go to longer time intervals, like twice the mean recurrence time, in this experiment, you have about a 60% chance of getting it right, 20% chance of being too low, and about 20% chance of being too high. And of course, we only ever get one of these. So the odds are good that a lot of what we think are probably not working. The last thing we don't have, many cases have much good idea is how strong the shake will be. And that's about the same difference as assuming the magnitude. The things they use are plots where you predict the amount of shaking as a function of distance. But it turns out that there are different models you can make of this. And so changing your shaking model is about the same as changing the magnitude of the earthquake by 1 unit. So here's kind of a fun example. This is, again, for the Midwest. Changing the magnitude of the earthquake from 7 to 8 changes the shaking by about a factor of 3. Changing the ground motion model changes it by about a factor of 2. And you haven't got a clue which of these are right. So finish up. What do we need to learn how to do that we haven't learned how to do yet? First thing is start to realistically assess uncertainties and present them. When these maps are shown to engineers or building officials, they act as though these things were truth. In fact, these are, as you see, they're wild uncertainties in this stuff. You can more or less make the earthquake hazard whatever you want it to be. The other thing we need to do, and this is something a lot of us are starting to talk with our statistical colleagues about, is how do we start testing these models anyway, objectively? So let me walk through this. As the climate people are clearly way ahead of us, in that at least they are showing, what was being talked about last time, they are showing these predictions of an ensemble of models. In this case, they're getting about a factor of 3. And what's even better is they're at least they're trying to acknowledge all the systematic errors that aren't in their models, even if they don't know what they are yet. We're not doing that at all. This is just an experiment I did for the models I showed you in this talk. And so, for example, the government's position is that Memphis is more dangerous than California. And the answer is, yeah, you can find a model in which that is the case. You can also easily find models in which are about a factor of 4 lower. And the answer is presumably somewhere in between these things. Testing, I think, again, it's something we tend not to do in geoscience. The need for it is kind of illustrated by what the medical community is starting to hit. They are just starting to test their models in what they call evidence-based medicine. And as most of you know, it's generated absolute fury. It's actually a big fight in Congress over this idea of evidence-based medicine. The doctors are very down. Some doctors are very down on this because there are things like they were doing 650,000 knee surgeries a year, or 5,000 each, and the outcomes appear to be absolutely no better than a placebo. So you can do the math: 650,000 times 5,000. And this is not at all uncommon. The same is true with a fair number of other drugs. We need some way to start testing these maps. As Dr. Geller pointed out in his paper, says his guess is it looks just without formal testing like the Japanese government's hazard mapping program, which is by far the most aggressive in the world, is absolutely no better than assuming the earthquake hazard is uniform everywhere in Japan. And I've been talking this too with colleagues who are here, who Spencer and there. It seems fairly clear that what happens is they're wildly over-parameterizing these models, and the models have essentially very little predictive value. This is the kind of parameterization they're doing. They cut, they slice the trench up into very detailed pieces, and they put different probabilities on each of them in different magnitudes. And as you can see, all of this proves to be completely wrong. The earthquake absolutely blew through all of this, completely, indifferent to any of the details of hazard mapping. It just all failed in one big earthquake, much, much bigger than any of their models. Testing challenges. The obvious one that people worry about is the short time history. We have ways of getting around that from these geologic records of earthquakes. We do it in some places. It's not perfect, but the bigger one is the following, and it gets very close to what Blake was talking about in his talk, that when you discuss this to statisticians, they say, well, okay, that's pretty easy. We'll take some slice of the data, we'll cut that piece out, we'll make a model and predict the other part of it. Yeah, that's what they have to do. The problem is that the maps, these earthquake hazard maps, are so subjective, and they have to make so many assumptions going into this that there's no objective way to make these maps. Given some set of data, there's no way to do it. So it's a totally subjective enterprise. So this is a huge problem we need to figure out how to get around. So summary here. We're not predicting earthquakes, and we're not predicting earthquake hazards very well. Sorry, we're not predicting earthquakes well, we're not predicting earthquake hazards well. Hazard mapping depends enormously on our preconceptions. There are huge uncertainties that are generally underestimated, and as far as I know, never communicated to the public. Sometimes we're too high, sometimes we're too low, and unless we start objectively testing these things, they aren't going to get any better. And the problem is it's not at all clear that people want these to be tested. There's a marvelous story when Kenneth Arrow, who went on to win the Nobel Prize in economics, was in the Army as a weather forecaster. So they made weather forecasts, month-long forecasts, and then they concluded they were absolutely no better than random. So they told the general this. The general said, well, the commanding general is aware that the forecasts are no good. However, he needs them for planning purposes. And this seems to be what has happened in the earthquake hazard business. People want to have maps of earthquake hazards, and they're much less concerned with what they're actually right about than they want to have some map. And so how to do better than this is a very tough question. But I think the first step comes in starting to acknowledge the problem that we have here. And I'll stop here. Thank you.
Question, Seth? Yes. So I gather from your repeating calls for objective testing that you know that CSEP efforts are inadequate.
Well, I don't think they've really confronted the sort of large-scale question. I'm not opposed to sort of what they're doing. I think what they're doing is a small step in the right direction. But they're making predictions that, again, they're dealing with very small rates of earthquakes. So, it doesn't, what we need to do is go back and somehow do like a much more sort of a macro scale sort of phenomenon, talking these hundreds or thousands of years. Because right now, I don't think from the CSEP stuff you could really say, well, first they're not doing hazards, they're doing rates. But even I'm not sure one could realistically say that, you could accept or reject sort of hazard maps based on this. I don't think we have the kind of, I think what we need is the kind of protocol that the meteorologists developed over, like, I don't know, starting in the 50s or whatever, where they at least sort of agreed on the set of tests as to how they were going to metric their forecasts. Are they doing better than, I think the first one is like, are they doing any better than saying the weather tomorrow is the same as the weather today? And the other one is, are they doing better than the long-term average of, like, October 2nd in Chicago, and is the forecast better than that? And they sort of agreed on a set of criteria they were to use for the synoptic forecast. And then they started building these. So I think we need to go that route. So I'm not saying I think what CSEP is doing is perfectly reasonable, but I think we need to do much, much further to do anything that will actually give us a way of doing it. It's not a criticism. Yeah.
You presented your case very well. I wonder if you might be able to present any kind of case for the people who say they can't predict. Is there a case? Or
prediction, there's one successful case in China in the 1970s where they had a very large increase in seismicity, and they did evacuate. They admit that they had a very large element of luck in that. Whenever you have areas where seismicity picks up, like there was a big one in Reno, Nevada a couple of years ago, and everyone said, oh, I don't know, maybe there'll be a big earthquake. It's perfectly plausible to say it didn't happen. But, I mean, the Italians actually tried to go back over the earthquake catalog of Italy and say, okay, what fraction of the time when you had an increase in local seismicity was it followed by a larger earthquake? And that was about 2% of the time. And that earthquake would have been a lot smaller than what happened in L'Aquila. So it's hard to say what if you did objectively, but you might have said there was a 0.1% chance. So if you do this often enough, occasionally you'll be right. But the problem is to decide whether you're getting better than random.
somebody wins the lottery.
What?
Somebody wins the lottery.
Yeah. John?
Yeah, I have a comment. So perhaps the analogy is not to evidence-based medicine, but rather to the prediction of So the methods for measuring electrocardiograms and EEGs are almost 100 years old. There is tremendous interest in being able to predict catastrophic events. I'm told absolutely no luck.
Ooh, that's very telling. That's right. And they presumably have good data, at least reasonable statistics on how well they do.
Much better data.
Yeah, much better data. Which is troubling, yeah.
I agree with all of your conclusions, but there's something about some statements you made that rubbed me the wrong way. And I think you're falling into the same trap that other people do about taking selected data. And that is looking at a place where an earthquake has happened and said that the probability that was estimated for that was low. The models all have large regions of relatively low probability that added up amount to significant probability. So virtually any of the models, the good ones and the bad ones, say some earthquakes are going to occur where the probability is low. That's not a failure of the model by itself. And when you look at the earthquake in Haiti, there are many, many other places around the world that have similarly low estimated probabilities, but some of those in the next decade are going to have magnitude 7 or larger earthquakes, and some of those will be nasty. So to take an earthquake that's happened and say the probability that was estimated for that is low, I don't think that's proper reasoning. You have to look at the winners and the losers, not just...
Oh, no, I certainly agree with that. I was using these as illustrations of a problem rather than as, obviously, one has to, this is the whole point, is to develop some objective method of testing these things that you agree with, so that, I mean, obviously you have a large enough area. One thing we've been toying with, taking this around, is to take a map of the world and imagine sort of expanding the region. Like, so for example, you might start off and you let the area grow and you see at what point the forecast starts to do better than saying it's uniform. So for example, it may very well be that within California, the models on individual faults aren't fantastically useful. On the other hand, as you grow the area, at some point it would certainly be true to say, that this would be more dangerous than Kansas, and to try to figure out where that transition is, which might give you some way of looking at sort of how parameterized it is. I think the point of the analogy is first that to try to get across the idea that there is a problem here, because as you know perfectly well, the official position of the U.S. government is there isn't a problem. The official position of the government is I believe we have high confidence in whatever the words they use in our earthquake hazard forecasting method. We're saying, well, I'm not quite sure why you have such confidence. It doesn't look that good to me. So yeah, I'm not disagreeing. Sorry.
Well, the basic approach is based on the belief that there is a way to predict, right? Because if there is no way to predict, there is no effort of the sort that is needed. Right? So what's the consequence? What do you think? Is there a way that we don't know to predict? Or maybe
to predict individual earthquakes, my guess is no. If to predict longer-term hazards, at some level we think, and this is the point of my expanding circle thing, at some point there probably is. I mean, we certainly, or I would say that yes, the probability of larger earthquakes is higher in California than it is in Chicago. So at some point there's some statements that can be made, and the question is to decide what level of statements can be justified and what can't.
But in terms of objects, that is like the stones in Japan. I mean, they measure the highest rate of what you came, and if you build above it, you're probably fine. I mean,
there they had that record. The question is, what about the other places where you don't have it?
No, the question is whether mathematics is useful in this regard.
I think the first thing is that I think that the statistics certainly will, in terms of the most, often the most useful thing to an outsider that statistical analysis can do is to try to tell you whether what you believe is actually true or not. Okay, and I think that would be a huge help for us. And this is a question that David was raising.
Also confuse you. But throwing numbers.
Fair enough. Fair enough.
There are some hypotheses that can be rejected out of hand. And statistics can certainly help you do a good job.
But you know, if we're, I think the point is that if we're going to be making, I mean, literally these are multi-billion-dollar decisions. If one is going to be making multi-billion-dollar policies, what we're hoping, at least we're trying to get some sense is that, you know, how good empirically or bad empirically or something. There's some criteria other than one's pure gut feelings. And right now, most of this is being done on pure gut feelings. And so I think that this is someplace where some sort of, like the weather forecasting, some sort of statistical techniques should be able to help us a lot in making kind of intelligent policies. But first, we need to know what we're doing.
Question from the
Seth, just as a comment, so basically these hazard maps do fairly well at knowing where earthquakes have been, but not where they will be. And again, there seems to be some logic there, maybe even ancient logic, of saying, okay, if I have to predict what tomorrow will be, I'll guess it's like today, or something of that level. And again, in that book, Future Babel, at the site on the bottom, they seem to have numerous examples of that, of people making forecasts, economic forecasts from the 1950s to the 1960s or whatnot, that pretty much are more reflective of what the time of that prediction is, not the future in any sense at all. But there is logic.
There is logic. Of course, that was my colleague in Middle-House comments. He said that the major thing you learned from earthquake hazard maps is the year they were made. They didn't tell you a whole lot about earthquake hazards. They told you about when they were made.
I just wanted to comment, is it a failure of the hazard map because of a large earthquake in an area that has low probability?
Well, that's the tough question. Obviously, the answer is any individual one, no, right?
All kinds of people experienced floods this year that were not at high risk of flooding. And I wouldn't say just because there was one flood that was larger than any flood in several hundred years that they're at a high.
No single failure tells you that. That's why one needs to try to develop a criteria for if you have you basically need to be looking at what get a large enough set of data to say that are these earthquakes happening? Is this the flood thing is like not whether you have a 100-year flood, but whether the 100-year flood is happening every 5th year. The 100-year flood, it tells you there's something wrong with the model. If on average once every 100 years you have a 100-year flood, it's not a failure of the model.
question from
There's a couple from the webinar. First one is from Mike, and he asks, what about some type of control, like using some type of explosive to trigger some faulting going on? Is there any way that you can do that?
Well, we know that at least under certain conditions, if you inject water in the fault zones, you can trigger earthquakes there. That's pretty commonly observed under dams, major dams. Whether that's something, I think most people feel it's not something we would understand well enough that we would actually want to try it ourselves.
model that.
Yeah. We can.
Model that numerically.
It's been modeled numerically. As you know, there's actually a controversy in China as to what extent reservoir filling may have had something to do with the Winslow earthquake. I think it's something that probably we wouldn't want to try ourselves with the state of our knowledge now.
And then the second one was possibility. Is there anything else that you can measure that isn't being measured right now?
Ooh, that's a tough one. I mean, it's hard to think of. The one that has been a constant bugaboo is the thought that there are some sort of electrical signals before earthquakes. That's never sort of, again, it always seems to be one of these, after an earthquake, someone says they saw something, and it's never reached the point where, like, you have a convincing correlation yet. You sure hate to say there are things that aren't happening, and the reason is this, that if you talk to highly intelligent people that work in laboratories, before rocks break in the laboratory, things happen. That seems to be, they're quite clear on that. On the other hand, in the Earth, it seems hard to see anything happening yet. And this disconnect has been around for 40 years now. We don't really have a good answer to this yet.
What about inside?
What?
What about inside?
Well, again, INSAR is just another way of measuring deformation. So, I mean, it's like, if you could see it with GPS, you could see it with INSAR. I mean, there are technical differences, but either we will turn out to see significant deformation deformate and break changes before earthquakes or not. So I mean, INSAR is just another, the conceptualization that's useful is, think of INSAR as putting a GPS receiver every 100 meters on the ground or something. So it offers you a better way of doing something rather than a conceptually different way. So again, we don't have any fantastic, compelling evidence of major changes beforehand. The same is true for stress changes and so on, like the strain meters or something. It seems hard to say, one needs to keep looking for these things. But so far, the track record has been kind of discouraging. Dave, would you have your take on this?
I agree entirely that you can make these measurements, and there are things that you see. Generally, they're better related to hydrological changes and other sort of things that happen close to the surface of the Earth. But there's been no success in relating any of those to later earthquakes. And the task of having a convincing relationship is really overwhelming because you need more than one example.